Order of business, remember that there is a homework due this week and there is a project that you're supposed to work on. I want to pressure you to try to get to it as soon as possible because there's a lot of work to do on that project. And I'll talk a little bit about techniques that you're going to, or a bit about the project because I'm going to introduce techniques that you're going to need for the completion of that project. Okay, so thus far we've covered a variety of topics that are of extreme relevance to understand everything that we're going to do in machine learning, starting with defining features. And your features are going to be dependent generally, although we'll get to that at the very end of the course. They're generally dependent on the problem that you are working on. So if you are working on speech recognition, you're going to have a certain type of features that you're going to define and work with. If you work in computer vision, there are going to be certain different set of features that you're going to work with. And if you are working on bioinformatics, then there is going to be yet another set of features that you're going to be working with. Once we have our features, we can define our feature space, right? And then once we obtain observations from the world, we define those observations with regard to those features in that feature space that we have defined. And now everything that we're going to do in machine learning is defined in that feature space. Okay. Now we've already seen several things that we can do in the feature space. Number one, we can compute the mean, the variance, the covariance matrix, or other statistics. Most importantly, the covariance matrix, which is related to the correlations of our samples, right? And that allows us to design algorithms to actually categorize objects or our samples in a set of categories, precisely because the samples of the same category are going to be equally correlated, right? Given the features or dimensions of our feature space. We also saw how to compute the principal components. That is the way of determining which subspace within our feature space defines the samples that we have, right? Now, in general, if P, remember P is the number of dimensions or features in your feature space. If P is larger than the number of samples, N, then your samples are always going to be defined in a subspace of your feature space, right? Because you have more dimensions than samples. And therefore, if you have 2 dimensions and 2 vectors, I mean, there would be P equal to N, right? The best you can represent with 2 feature vectors is a line, which is 1-dimensional, right? The best in general that you can represent with n vectors, it's n minus 1 dimensions, right? Okay, so there's always going to be that. And we'll see that PCA obviously has an application in that case, and it's very common to first apply PCA to your data to eliminate the dimensions that are irrelevant for representing your samples, but also to eliminate noise, as we discussed, where you keep a percentage of the variance of the data, right, between 70 to 99% generally, and other applications that we will discuss. But I want to stay for a moment with the concept of the covariance matrix that we have computed. And before I go on, I would like to say everything that we're going to see in the next 2-3 weeks now is going to be a part of machine learning and pattern recognition that is included in what's called probabilistic methods. This is also part of generative algorithms, okay? So probabilistic methods are going to be using distributions and probabilities that we're going to start working with today. And generative comes from a word that once you know that distribution, the underlying distribution of your data, you can generate as many samples, observations that you haven't seen as you want to. right? So we'll get to all these details, but let's just start with the definition that we had of our covariance matrix sigma x, right? So remember that sigma x defines the variances in the diagonal and the covariances in the off diagonal of all the features fi and fj. Now, why is that important? Let's remember what a metric space is. Now, I know that you're all very familiar with this, but in general, if you have an M matrix, and M is symmetric and positive defined, right? So this is symmetric and positive defined matrix, then that matrix M specifies the metric of our space, right? And the metric can be given, let's call it d square of two vectors, say xi and xj. These are xi vector, xj vector. Given my metric or matrix M that defines a metric, then that's equal to xi minus xj transpose M inverse xi minus xj, right? You know that. We've seen that before in many classes. Now, this defines a normed vector space, right? So a normed vector space is given by a specific norm, right? When that norm, so this is nothing else again than a vector space of basis vectors, right? Remember that from image processing. A vector space, and the norm is given in that particular case by a symmetric positive definite matrix or a quadratic equation, right? So in that case, we talk about the Hilbert space. Right? So the Euclidean space, the real domain, all these spaces are Hilbert spaces. Okay. Now, more generally, a normed space, vector space that is complete is a Banach space, right? Now, if you will remember from our first lecture that I mentioned the Banach-Tarski paradox, and you have a ball in 3D space, right? You have a ball, and you partition it in a number of finite pieces, and you translate these pieces, you put them back together in that with two balls of the same size. That's the same Banach, right? These are the giants of functional analysis. So this is a Banach space, any normed vector space. The Hilbert space, again, is a particular case that we'll be working with, which is specified by an inner product and therefore by a symmetric positive definite matrix. All right. What happens if, let's see some examples of this. What happens in the particular case that my matrix M is equal to the identity matrix? Then what do I have here? What's that? The square, okay, what's this called? So when M is equal to 1, that specifies a specific norm and a specific space. What are those? What's that? The two norm. And what's the space? The Euclidean space. Very good. Right? So when M is equal to the identity matrix, this is the two norm that we're very familiar with. and therefore that defines the Euclidean space. So why is that? Let's think about this. So let's think that we have our feature space. It's two-dimensional, right? And our matrix M in 2D would be equal to 1, 0, 0, 1, right? The identity matrix. And what that means is that for the first dimension, when it moves about the first dimension, it has a weight of 1. And when I move about the second dimension, it has the same weight, right? So that's generally represented with a circle, right? S1. And that circle just means that all the points on the surface of that circle, right, are at equal distance from the origin of that coordinate system, right? So let's see what happens when I have a more interesting case. So remember what we have computed in our feature space. We have a number of data points, right? And from these data points, we have computed the covariance matrix. So the covariance matrix represents the data that we have collected, right? And now we want to use this to define the norm or the metric of our space. So what happens when I have M in that case here? M equals to the covariance matrix, right? That's what we're interested in. So to see this, let's do an eigenvalue decomposition of sigma x. So remember sigma x, V, it's equal to V capital lambda. Capital V is the matrix whose columns are the eigenvectors, and lambda, it's a diagonal matrix of corresponding eigenvalues, as always. And now, once we have these eigenvectors, we can project our data. Let's call it our data. So we have our data points here, the xi's, right, vectors. So let's call it capital matrix X, which is x1 through xn, right? So we have done before. So I can compute y as the projection of my samples x onto my PCA space, right? And all this does, remember, is that identifies, so first, this centers this coordinate system on the mean of my data, right? Because I subtract the mean. And then it computes the eigenvectors, which are the basis vectors that specify the dimensions of maximum variance, which are this one, right? In this case, V1, V2. And once I have this, right? Now, if I apply this transformation, all I do is I subtract the mean and I rotate my space, right? Such that this axis here, right? Defined, let's say by I, or let's not use I, let's use maybe E sub 1, and this basis vector E sub 2, right? This is rotated such that it aligns with V1, and this one is rotated to align with V2, right? So the resulting space is going to have the same data points here, but they're going to be now like this, right? So what does this mean? Well, let's think about this. It means that I am now applying, if I compute the covariance matrix of Y, I am applying to it the transformation of the eigenvectors. So this is going to be equal to, anyone? Okay, I'll give you a hint. I start with sigma x, right? And I apply this transformation. So I do V transpose sigma x V, and V transpose V, it's the identity matrix, right? Because they are basis vectors. So this sigma y is equal to lambda, right? Capital lambda. And therefore, sigma y, it's a diagonal matrix, right? Okay, so let's see what that means. In the Euclidean space, this distance here, the d square, meant that I sum over the different entries of my vectors, right? So I sum over the x I, or sorry, not x. Let's see, I have xi and xj, so I'm going to sum over, let's say, k. So for every k, right, the xik minus xjk square, right? This is what this means, right? Now what happens here? Well, what really happens here is that the d square is going to be equal to the sum, as does, of xik minus xjk square. But obviously here there was a multiplier, scalar, because I'm multiplying by the matrix M, right? So when I do the first one by the second one, I multiply this by this scalar, right? 1. So there's a multiplier of 1 that we've omitted here, right? Obviously. But here we can no longer omit this, right? This is going to be my lambda, right? My lambda k, the eigenvalue. And therefore, if I apply this, this is nothing else than a weighted version of the Euclidean distance, right? So this is a weighted version of the Euclidean distance. Okay. Excellent. Now note that I could actually transform this even further, right? I could now compute z, another variable z, where sigma x v transpose v, remember, is sigma y, right? We know that. But now I could multiply by capital lambda negative 1/2, capital lambda negative 1/2 on both sides, right? Because this was equal to lambda. Now I have lambda 1/2 inverse, lambda 1/2 inverse on each side. So this is equal to the identity matrix, right? And therefore, the distance for this new space is back to the Euclidean distance, right? I've eliminated the weights, right? This process here, these two processes, are called diagonalization in the first case, when I do this first step here, right? This one. This is called diagonalizing the matrix, or diagonalization. And this one down here, that gives me sigma z equal to the identity matrix, right? This is called whitening, okay? And it's called whitening. It comes from signal processing because of the identity matrix, meaning that you have white noise in signal processing, okay? And this is sometimes called, obviously, the whitening transform. All right, so let's go back to, yeah, question? this Z here? Oh, I'm sorry. Yeah, you're right. Thank you. All right, so where were we? Yeah, so let's go back to this, right? So we had originally, when M is our identity matrix, right? We have the circle, meaning that when I move about this dimension and about this dimension, it carries the exact same cost. That cost is 1, right? Has the same weight. Doesn't change for different k, for different dimensions, right? But when I have this case, right, the diagonal matrix, it means that it costs me more to move about one of these dimensions, say this one, right? Then it costs me to move about this one, so lambda 1, lambda 2. And that is given by this ellipsoid, right? Right? And if I now rotate this back to the original axes of the basis vectors, then I end up with yet another ellipsoid that is rotated given my eigenvectors, right? V1 and V2. You see that? So that just basically tells you how much it costs to move from one in every single dimension in your feature space. I'm not following you. Multiplied by y. By sigma y, you mean? Oh, z would be the same thing as this equation, but now you have to multiply by the lambda here, right? The inverse of the lambda. Is that what you're asking? Yep. Minus half. All right. So what this really represents here, right? What this thing that we have here represents, this final ellipse that I have drawn here represents the distribution of my data here, right? So this is the distribution of the data, right, that I have given. So see this here? This data gives me the covariance matrix, which gives me the metric, which basically tells me how this data is distributed in my space, and therefore I can compute my metric. Okay? Now, what the specific distribution is given by the first moments, the mean, and the second moments, the covariance matrix of the data, the normal distribution, right? The normal distribution is specifically given by the first and the second moments, and that's exactly what this represents, right? Now, to be precise, we'd have to draw this two-dimensional space that I have here, okay, with my ellipse that I have here. And now I should add a third dimension that specifies the probability, right? So this would be something that looks rather like this in 3D, right? So this would be in 3D, right? So this is a mountain, a Gaussian, right? That specifies the density at each point of my two-dimensional space, right? So that's the PDF of the normal distribution specifies what is the probability of finding points in certain areas of my space, right? Now, obviously, in the normal distribution, it says that at the mean, that's the most probable area. And as I go away from the mean, that probability decreases, right? All right, so the normal distribution then is given by the following PDF, my function of x given mu and sigma x, my two parameters. These are called the parameters of my distribution, right? And therefore, we will be talking a lot about parametric methods, meaning that we are using parametric distributions. These are the parameters. So given that this is equal to Cn sigma x times the exponential function of -1/2 d square x mu, where d square is this equation right here with sigma x as my metric, right? Okay. And Cn, it's the normalizing constant. Remember that all the PDFs, when I integrate them, have to have volume equal 1. And to do that, I need to have a normalizing constant, Cn in that case, which for the multimodal Gaussian distribution is 2 pi to the power of -p12 times sigma x to the power of -1/2. Okay? And again, that's called the normalizing constant. That guarantees that when I integrate my PDF, the volume is going to be equal to 1. Now, we'll be using in machine learning the Gaussian distribution a lot. It's not the only distribution we're going to use. That is a main distribution that we're going to use. And there's a big reason for that. And the main reason for that is a very famous theorem called the central limit theorem. Which, in short, you've seen that before in random variables, right? A course that you've taken before this one. Just basically it says that if I have a set of observations x1, x2, up to xp, p the number of dimensions, or actually rather the different types of observations or dimensions, doesn't matter, that are IID, right? So they have to be independent and identically distributed. And we assume for simplicity that these are scalar random variables. And you may assume that they have a common underlying PDF, okay, whatever that is. It doesn't matter. Just some underlying distribution. All right. We're also going to assume that their mean is 0 for simplicity. And then that theorem basically says that if I now compute the distribution of a new variable, zi, which is the combination of my observations x, right? So zi is equal to x1 plus x2 and so on, right? And I normalize this by the variances just to make everything nice. Actually, one. Then, oops, I'm sorry, my bad. This is squared. And now I take the square root here. Then the distribution of this new variable is going to be the Gaussian distribution, the normal distribution, right? So in effect, when I have lots and lots of observable variables, IID variables, so when p tends to infinite, right, then the distribution, the PDF of my xi, so xi's are drawn from this PDF, that PDF of the Zn is equal to the Gaussian distribution, or phi z, where phi z is the exponential function to the power of negative x squared over 2, right? Okay. So let's see how this works. More than this, which you have already seen in 804, I think it's more important to actually understand what this means. So consider that these xi's are drawn from a step function, right? Step function looks something like this. It's 1 in some area of my space, and I'm considering here just one single dimensional space for each xi. So this is for each xi, right? For each xi, I have a step function, the same step function. And now I want to compute the distribution of all the xi's combined. Now when I have several signals, I combine them, meaning I add them together, right? And then what happens? Well, for the PDF, these are convolutions, right? It means that each PDF is multiplied with every other PDF at every possible location, right? AKA a convolution, right? So let's see what happens when I do that. So imagine that I start with xi and xj. So my xj is going to have another step function that I need to multiply with this first one, right? Now when I multiply them like this, right, they're shifted, right? Then what do I obtain in that multiplication? 0, right? Because this one is multiplied by 0, this one is multiplied by 0, so I get 0, right? I don't get anything. Agree? But as I shift this toward this, because that's what the convolution does, right? It multiplies at every possible location. So when I shift this or in this direction, I'll be a point where I start getting into that region of the other distribution, and that will give me some volume, right? Just small volume. And as I keep moving inwards, I will get more area, and that will increase linearly, right? Until they are both one on top of each other, right? Where the area will be the max. And then after that, it's going to start leaving this region, so it's going to start decreasing linearly again. And that's going to be the new PDF of xi and xj combined, right? Now, I have this one, and I have another one for xk, right? And again, this is, of course, still a step function because they're all drawn from the same underlying distribution. And when I do this and they're not aligned, this is 0. But when this is moved over here, this is a small region that they have in common. So this is the value that I'm going to get. So it's going to increase like this. And now look that when I move this inwards, this area grows exponentially, right? So that will grow something like this to the peak, and then it will decrease like this. Not a Gaussian, but pretty close to a Gaussian already. Started with step function. After 2 steps, I'm already at almost a Gaussian, right? So obviously it's not a Gaussian because this is 0, and a Gaussian cannot have zeros, right? It goes to infinity, but it gets really close really quickly. So the idea of using the normal distribution is as follows. In most problems in machine learning, we observe a specific set of variables, right? But those set of variables, remember, are nothing else. We've seen this already. Our observed variables are nothing else than some linear or even nonlinear combination of some hidden variables, right? The latent space that's unobservable, right? Now, what we see, it's X. We don't see S. We wish we had S, but we don't even know what S is, let alone observe it. So, in general, when you take an image, there are a lot of variables that are involved in creating that image. When you put a microphone and you record sound, when you record information from the biological world, and so on, there are a lot of hidden variables that you don't control, but these hidden variables give you X, and that X, therefore, it's a combination of these hidden variables. And if I combine these hidden variables, I generally obtain a normal distribution. That's why we generally work with normal distributions, right? Okay? Now, the obvious exception is when I want to working with this model and having my observations X, I don't want to do an analysis on X, but I actually want to know what the sources are, right? I mean, wouldn't you in some applications be interested on what these sources are? So let me give you an example that we've already discussed. If I'm in a room, right, at a party, and 10 people are talking at the same time, and I put a microphone right there, and I record that data, I'm going to get a sound signal that is the combination of 10 people speaking at the same time. Am I interested in that observation X? No, of course not. I'm interested in the 10 different signals, the 10 different sounds or words or sentences that people are speaking. I'm not interested in the combination of the signals. It's meaningless to me, right? So in many applications that happens, right? How can we recover? In the slide you have another application. It's really cool. Really cool application in computer vision or image processing, where you take a picture of someone looking, say, at a framed painting, let's say, okay, or maybe someone looking at a store from the outside, right? So there is a mirror or a glass that separates the store or the whatever it's in display and that person, right? Or you have a painting which is covered with a glass, and then you're looking at this, right? And you take a picture. And when you take a picture, the painting is going to show with a superimposed image of the person looking at it, because that person is reflected on top of that glass, right? As if it were a mirror. You have now two hidden variables or latent variables, right? One is the information of the or the pixel values of the painting, and another one is the information of the person looking at that painting. What you observe, it's a combination of the two. But what you're interested in is in teasing them apart and analyzing each one independently, right? But how do you do that? So this is a huge problem in pattern analysis. How are we ever going to recover the sources? And we already talked about a method to do that that's called factor analysis that we'll come back to when we have more knowledge about or more tools to address it. But right now, I want to talk about the technique that is very useful to recover the sources, which is called independent component analysis, or ICA. So again, we start with this model, x equals AS. So we assume that I have an observation x that is a linear combination of my sources. For simplicity here, let's say, as always, I'm going to say x is in RP and s is in RQ. For simplicity right now, I'm going to assume p is equal to q. We will get back to this. What that means, for example, if 10 people are talking at the same time in that party that we were discussing, and we recover the 10 different signals, I need 10 microphones. That's what that means, right? We'll get back to that problem of what happens when Q is actually of higher dimensionality than P. That's a problem that has not been solved until very recently, believe it or not. Okay? But let's, for simplicity, assume that I have 10 microphones by some magic. I'm also going to assume, let's see, what else am I going to assume? I'm also going to assume generally that the expected value of the sources is 0. So they're mean-centered, right, or mean-normalized. And so generally, I'm going to assume that both the expected values are 0. And my goal, let's define the goal first. Maybe that will simplify things. The goal is to estimate A, right? So find A. That's my goal. Because if I have A, given X, I can find S. Or given S, I can find A, right? So that's what I really want to find. A is unknown. Now, the distribution of X, the underlying distribution of X, is unknown to me. Although, from the central limit theorem, I can assume it's a Gaussian, right? And the distribution of S is unknown to me as well. But from the central limit theorem, I can assume it is what? New one? Gaussian? Really? I think generally I can assume it's anything but Gaussian. Right? I mean, is it the case that is it possible that they are Gaussian? It's possible, but given the large number of possible distributions that I can have, what are the chances that they're Gaussian, right? Now, when I combine different distributions, yeah, I do get a Gaussian. So X is probably Gaussianly distributed, but S, if anything, it's anything but Gaussian, right? So we'll talk about this. Now, I can only note, that's important, note that I can only recover A up to a scale. Anyone can tell me why? Why can I only recover A, capital A, up to scale? Anyone? What happens if I multiply A by a scalar? Then I need to divide S, my source, by the same scalar, right? But I don't know the source, right? So if I recover sigma A for some sigma larger than 0, right? How am I going to know that the S I then imply or recover from that A, right? So given X and A that I have recovered now, I can compute S, but then that S is going to multiply by the same scalar, right? So my goal is to find A up to scale. There's another limitation that It's given by this equation, right? Now remember that when I use PCA, right, in principal components analysis, I can actually recover the order of the PCs, meaning from most variance to least variance, right? But here I can't. And the reason is that I can come up with a permutation matrix, right? So same, I can multiply A by the inverse of a permutation matrix. Permutation matrix is a matrix that permutes the columns or the rows, right? Like it's columns of a matrix, right? It interchanges the columns of a matrix from one place to another, right? I with J. And then again, PS, right? And then obviously, how am I ever going to know? There's just no way I can ever recover that. So that would just give me a new A and S. Let's call them, I don't know, A tilde, S tilde, right? And those are the ones I'm going to recover. So that I have to know that this is not recoverable. OK, good. So let's see. How are we going to solve this? We already know of a technique that we can use, which is called principal components analysis, right? Or eigenvalue decomposition. So can we use an eigenvalue decomposition on my data? Let's see. Imagine that my source vectors are these two, S1 and, OK, let me do this a little better, because these are almost orthogonal. All right, I'll do this, S1 and S2, OK? So these two define this dimension and that other dimension, right? OK? You see that? And now, when I get my observations, I'm going to get points here, right? So these are my feature vectors. OK. Now, I want to recover S1 and S2. So what I'm going to do to recover this, I'm going to use a technique I already know called PCA, or an eigenvalue decomposition of my data. So I'm going to compute my covariance matrix of sigma. I'm going to compute sigma x of my data x, right? And then I'm going to do an eigenvalue decomposition. And what's that going to give me? Well, the direction of maximum variance is this one. You agree? So V1 is going to be this one, V1. And the second one, V2, has to be orthogonal. So it's going to be this one. So that's the original space. Obviously, that's not S1 and S2, right? And the reason for this is because an eigenvalue decomposition, or PCA, can only transform the data linearly, right? It can only rotate the space. I can translate by subtracting the mean in the covariance matrix, right? So the origin is translated to the mean, fine. I can rotate the space, right? So if my original basis vectors are these two, and my eigenvectors are like this, I rotate the space to align the original basis vectors with the eigenvectors. And that's it, right? So it's a rigid transformation. But here, note that because S1 and S2 are independent from one another, I can recover them. And the issue is that independence is something stronger than correlation. So PCA is based on the idea of correlations, right? Remember that? Now, correlations and independence are not generally the same. Now there's a particular case in which correlation and independence are the same. Think about this. I'll ask you in a second. But let's see why this is so. So remember, if I compute the expected value of two variables, my joint expected value of two variables, x and y, right? So what I have here are two random variables. X and y. Oops. That are independent. And independent means that if I compute the joint distribution of x and y, this is equal to the marginal distributions, right? So this is equal to the marginal distribution of px of x times py of y, right? That's what independence means, right? So if I now compute the expected value of this, but before doing that, I apply to these variables, I apply a transformation, let's call it G and F, okay? Where G and F are linear functions, okay? And let's probably even say that they are linear functions absolutely differentiable in the space that I'm at, okay? So linear and differentiable, absolutely differentiable. Okay, then if I have this and I expand this result here, where's this equal to? This is the same as integrating g of x times f of y times the joint probability of xy dx dy, right? And then, of course, I integrate from negative infinity to infinity, right? And that's how I, this is how I compute the expected value, right? That's how we've always done it. And then, precisely because these are linear functions, I can rewrite this as integrating the first one, gx of px of x, right? Excuse me, linear functions, because they are independent variables, right? I can write pf of x here, dx, times the integration from negative infinity to infinity of f of y, py of y, dy. And now, what's this first term equal to? Anyone? This is the expected value of gx. And this thing here is the expected value of fy, correct? Yeah? And what have we shown? Well, we have shown that because x and y are uncorrelated, right, then this expected value is the same as this, right? But that is when these two functions are linear, right? So if I have two linear functions and the two variables x and y are uncorrelated, then the second order statistics of the data, right, are equal to the moments, first moments of the data, right? That means they are uncorrelated. Now, when they are independent, but that function is a nonlinear function, and that equality still holds, then we say that these two vectors are not uncorrelated, but independent from one another. So in fact, independence means non-linearly uncorrelated. That's what it really means. Okay? Now, as I said, there is a particular case for which uncorrelatedness and independence is exactly the same thing. Anyone knows the answer? There is a particular case for xy drawn from a very specific distribution, f, and in that case, uncorrelatedness and independence means exactly the same thing. What distribution is that? Is that the normal? Excellent, right? That's the normal distribution. So if that data is normally distributed, let's say with zero mean as we've stated, and I'm going to assume, I know, covariance matrix sigma, right? That means, let's assume that sigma is the diagonal matrix, so, or it has been diagonalized, basically. Then I have sigma x squared, sigma y squared, 0, 0, right? That's my diagonalized covariance matrix. If it's not, then you already know how to diagonalize it here, right? Then what are the correlations that I have defined here, right? Remember these row values that we had defined in the covariance matrix that specify the correlation? Well, they are both 0, right? So they are uncorrelated. And yeah, they are independent and uncorrelated. That's what the normal distribution does, right? So if I want to find independent variables, what do I have to find? Variables that are drawn from any distribution but the Gaussian distribution, precisely. If they are from the Gaussian distribution, then I'm stuck because all I can do with the Gaussian distribution is do an eigenvalue decomposition, right? I can only rotate that rigidly, the moments that I have. But what this is telling me is that in the Gaussian case, independence is equal to correlateness, right? Or uncorrelatedness. Sure. Okay. So how are we going to do all this? To do this, we're going to use something that's called the cumulants. Now the cumulants, I'm not going to cover it in detail. I think suffices to say, I'll cover them briefly, but suffices to say that they are they're related to the moments of the data, and it's so the cumulant of order k, it's the same as the moment of order k plus minus polynomial of the other order, or moments of lower order than itself. So let's see that very briefly. And the reason people work with cumulants is because it's easier to get the results, the mathematical results that you need to get in ICA. We usually call this mathematical convenience, meaning that's what allows us to derive our algorithms to make them sound formally and work in practice. All right, so let's see that, the cumulants. So our first goal is to understand how we can use the idea of independence, not uncorrelated, but non-linearly uncorrelated, or independence, to find the sources S in our model, right? I erased that. Let me write it again, because this is the model we are working with. X equals AS, right? Super important to remember this model. So as always, x is zero mean, a scalar random variable, as we have defined before, and its distribution, marginal distribution, px of x, okay? And now we define the first characteristic function. Now the characteristic function, recall, is a function such that if A is in B, so the characteristic function of, how am I going to say this? The characteristic function of A, of a space A that's embedded in B, is going to be equal to 1 whenever I'm in that subset A, and 0 everything else in B. Okay? So the characteristic function, the first characteristic function, let's call it phi of omega, that is equal to the integration of the exponential function of j. That j is the complex numbers, so this is square root of -1 omega x times the marginal probability. Okay? All right, so that's a definition of the characteristic function. This characteristic function is equal to the expected value of, anyone? The expected value of this part, right? Yeah? Okay, so the expected value of the exponential j omega x. Excellent. Now we're going to take the Taylor expansion of this to be able to work with that. Maybe if I must be really accurate, rather than the Taylor expansion, you can say the Maclaurin expansion. These are details, not important, which is the same as the Taylor expansion, but for series, right, of functions. So I'm going to take this about the value 0. And that is equal to the sum from 0 to infinite of what's this k, this Greek k letter called? Kappa? Okay, kappa, thanks. I never remember my Greek letters. Sub k, I just want to make sure that we don't confuse it. Kappa sub k of j omega to the power of k, factorial. Okay. So if I take the Taylor expansion of this, that's what I get. And the cumulants are these little guys here. These are called the cumulants. Okay. Responsibilities. The what then? Okay. All right. So if we use that, then you can show that the first cumulant is 0. Easy enough to remember, right? And then, of course, remember that we have assumed our mean is 0, right? So this is 0 mean. Our second cumulant is the same as the expected value of x squared. That means the second moments of the data. So the second cumulant is actually the second moments of the data. The third cumulant is equal to the third moments of the data, exactly the same. And the fourth cumulant, it's equal to the fourth moments of the data minus, remember I said that in some cases this is after 3, there is a polynomial of the previous moments. And for the fourth cumulant, this is equal to 3. The expected value of x2 square, actually cube, no, square. Okay. And so on, right? You can compute more cumulants. We'll stop at 4. And we'll stop at 4 because we want to use this one. We want to use the cumulants of order 4. In particular, this people call this the kurtosis. And generally, you'll see it written as the Kurt of x equals the fourth moments minus 3 times the expected value of the second moments cube. Oh, actually square. I keep thinking it's cube, it's square. Sometimes, actually more often than not, you will see a normalized version, right? A normalized kurtosis, I don't know, maybe bar, which divides this by this second element here. So you have E, the expected value of the fourth moments and the second moment square minus 3. You'll see this quite often. Okay. Now, this kurtosis if x1 and x2 are independent, then the kurtosis of x1 plus x2 is equal to the kurtosis of x1 plus the kurtosis of x2. Okay? Now that does not mean that this is a linear function. Actually, it's not a linear function, because if I have the kurtosis of alpha x, this is actually equal to alpha to the fourth times the kurtosis of x. Okay? So it's not a linear function, but if x and y are independent, then the kurtosis of x1 plus x2 is equal to the kurtosis of x1 plus the kurtosis of x2. All right. Any questions thus far? Yes, question. Independence infers that, right? Well, we'll get to that, yeah. So you're going to use that to find independence, in fact, right? Well, we'll get to that. It depends on the type of distribution, right? So that's what we're going to get at next. All right, so I know this was a lot to digest, right? A lot of new material. But the important thing to remember, the important things, is PCA does uncorrelatedness, right? It uncorrelates the data, right? That's what whitening is all about. But is unable to find nonlinear uncorrelatedness when these functions are nonlinear. For that, we need to turn to independence. That is very useful for us, because if we assume that these sources are independent, right, which is a generally good assumption. In the two examples I gave you, 10 people talking at the same time, their wave function, right, their speech, is independent from one another, right? I mean, unless they are synchronized and singing together in a choir or something like that. Obviously, they are independent. When I take a picture, right, of someone looking at a painting covered with glass, then I get the combination of these two images, and I want to separate them. Obviously, these two original signals are independent, right? Okay. So we want to recover this with the knowledge that these sources are independent, with the knowledge that this distribution may be Gaussian, but these ones are not Gaussian. Now, let's see what types of distributions we can work with. There are two main types of distributions other than the Gaussian. They are called Subgaussian and Supergaussian. All right, so the fourth moment of the Gaussian distribution is equal to 3, right? If you don't know that, it's 3. And therefore, the kurtosis is 0. I mean, that's just how we have defined things, right? But that's not true for other distributions. And the question that I guess we need to address is what does the kurtosis really represent? Or the fourth moment. So let's think about this for a second. The mean, the first moments of the data, represent the point of highest density in a normal distribution, right? Right? It means that's the arithmetic mean that if I take all my points, right, then on average, that's what I get. The variance is how much I deviate from that maximum point of density, right? Yep. So how far away are most of the points from that mean? Higher variance means that most of my feature vectors are really far away from its mean, right, or from the mean of distribution, but the smaller variance are very close, right? Now, the fourth moment would be like the variance of the variance, so to speak, right? And what that really means is how much the variance changes over time, which in a distribution means how heavy or tall the ends of the distribution are. Okay? Because of this thickness of this distribution, that heaviness, that's called in mathematics, that heaviness of these tails of the distribution is going to have a higher peak, or it's going to be more peaky or less peaky, right? It's going to peak more rapidly or less rapidly, right? Now, there are exceptions to that. We're talking very generally. There are exceptions in which case you can have really high kurtosis and the distribution is not super peaky, doesn't peak really fast. But those are general terms. In general, it defines the peakiness, or how peaky a distribution, or how much it peaks. Okay. All right, I think we're out of time, aren't we? No, we have 4 more minutes. Okay. Good. So let's think about a specific distribution other than the Gaussian. So we already know the Gaussian, right? The Gaussian looks something like this. Right? That's the Gaussian distribution. Now let's see what happens for some other distribution. I'm going to consider the Laplacian distribution. Which is given by the PDF, has 2 parameters, the mean, mu, and a parameter b. And this is 1 over to be the exponential of negative x minus mu. So I subtract the mean over b. Okay? Now here it is. So now the Laplacian distribution, if you plot it, looks something like this. So it peaks taller, faster, and as a consequence, it has what's called heavy tails, meaning that the distance between the tail of a Gaussian and of that of a Laplacian, right, are different. One is thinner, the other one is heavier, right? The Laplacian is heavier in that case. So positive kurtosis implies that you have heavier tails or thicker tails. And by thicker or heavier, we mean heavier than those of the Gaussian. Okay? So that means that the probability that you're going to find a feature vector in that area of your feature space is higher for the Laplacian than it is for the Gaussian, right? Okay. These distributions are called Supergaussian. So these that have heavier tails here, right? Like the Laplacian, the logistic regression would be another, the logistic distribution, excuse me, would be another Supergaussian distribution, okay? Now you can have the opposite. You could have distributions that are actually flat or have very low, very thin tails, right? Like we've seen one, the step function, right? Or the semicircle. The semicircle is 0 everywhere except the semicircle at some center point mu, right? These distributions are Subgaussian because the tails are actually less thick or heavy than those of the Gaussian. Okay? So what we want to do now, we want to use all this knowledge to see how we can find the sources. Remember, our goal was to find A, right? Because that's going to allow us to obtain our sources, because we have x equals AS, which means that S is equal to A inverse x, right? So that's what I want. To get to this, I need to find A up to scale and up to a permutation, right? Okay. Now, the first thing that I need to do is to I need to prove that I can use the cumulants, and in particular this of the fourth order cumulant, or the kurtosis, to find the sources, right? Meaning that if, as someone asked before, if I find this kurtosis, right, these values for which I obtain a specific value of the kurtosis, that result will correspond with my sources, right? That's what I need to prove. All right, I'll do that in our next lecture because now I am out of time. Make sure you review all that we've covered today. I know it's a